So in this webinar I'm going to be describing the range of different advanced nanomechanical characterization techniques that we have available in the Micro Materials NanoTest system. So when we think of nanomechanics, we typically think just of nano-indentation, but it's not the only useful nanomechanical test technique, and there's a lot of benefit to expanding the test window to include other nanomechanical test techniques, and I'll be describing those through the presentation. So I'll begin by talking about nano-indentation, and then I'll introduce the basics of the technique, and then I'll move on to looking at the influence of test environment on the mechanical properties of the materials that you measure, and I'll particularly look at the influence of humidity or moisture, the influence of strain rate, which we probe with nano-impact testing, and the influence of temperature. In this case, I'll just focus on high temperature testing. And then I'll finish off with a few slides on nano and micro-scale tribological testing that we can do, or nano-scratch and nano-wear. Okay, so a typical nano-indentation test involves applying a force to a probe. It can be a pyramidal geometry as shown here, or it can be a spherical geometry as shown here, or lots of other different geometries, and then that provides a load displacement curve that we then analyze to determine some mechanical properties, which I'll describe later. Additionally, if we move the sample stage as we're applying that force, we create some scratch tests. This is an example here shown for a hard titanium nitride coating on a silicon wafer with some very clear failure mechanisms. Or, as we're applying the force, we could reciprocate or do bidirectional stage motion, and that allows us to look at either fretting wear or reciprocating wear. And in the final technique, we can also apply an impulse to the probe, pull it off the surface, and fire it in at very high strain rate to create a true impact to the surface. And this example here in the bottom left shows an impact crater of into a optical coating, essentially, which has failed in this case. So if we do this repetitively, we can look at fatigue and fracture behavior. And all of these things are possible with the test instrumentation, which is shown at the bottom, the Micro Materials NanoTest Vantage. So the instrument has a range of different nano and micro-scale mechanical and tribological test techniques. So these 4 different measurement modules: nano-indentation, nano-scratch and wear, nano-impact and nano-fretting. But I think the key thing is, alongside that, is that we can perform these tests over a wide range of different environmental conditions. We can do the tests at high temperature up to 750 degrees Celsius. We can reduce the test temperature below ambient down to about -20 degrees. We can perform in controlled moisture, either fully immersed in various liquids for biomedical applications, or we can change the humidity for different other applications, or indeed we can look at the effects of different atmospheres on the testing and suppress oxidation of samples that way, which is particularly important for high temperature testing. Okay, so I'll start with nano-indentation. So a nano-indentation curve, it's a good idea maybe to think of it as a mechanical fingerprint for a material. So typically in a nano-indentation curve we apply a load or a force progressively into the material, and we load up, in this case an example here on the right, on a glass sample. And at some point we reach a preset maximum load or depth. We then hold either for no time at all or for a certain amount of time, which allows us to look at time-dependent behavior, and it also improves the accuracy of the unloading curve analysis. And when we unload, we get some elastic recovery in that material. And that elastic recovery, that hysteresis in the curve, depends on the hardness and the modulus of the material as well. So that's why you can think of it as a mechanical fingerprint. So on a very hard and elastic material, such as an amorphous glass or a hard carbon coating, we typically get a very high degree of recovery, which relates to a very high ratio of hardness to modulus in the material. If we are testing a soft metal, in contrast, we would get very little elastic recovery, and that's because there's a much smaller ratio of hardness to stiffness in those materials. So materials such as copper or aluminium have a much lower hardness modulus ratio, and that affects their tribological behavior. So with nano-indentation, you can get a wealth of different information. The two properties at the top, the hardness or the mean pressure and the stiffness or the elastic modulus, are perhaps the most commonly analyzed parameters, but there's also a lot of information you can gain on creep behavior. You can get stress-strain behavior. You can get information about the fracture toughness. You can get information about the yield stress and also the energies involved in the indentation test, the elastic and plastic work, and the partitioning between them, which is a plasticity index which relates to tribological behavior. So typically, or most commonly, the unloading curve is analyzed, and that with a power law fit to the tangent to determine the tangent to that curve, which allows us to determine the contact stiffness. And the equations then from the contact stiffness to derive the projected contact area and this reduced modulus are really quite simple. Once we have this reduced modulus, if we know the Poisson's ratio of the indenter and the sample and the Poisson's ratio of the elastic properties of the indenter, it's trivial therefore to determine the elastic or Young's modulus of the sample in question. And with this projected contact area, and since we know the peak load, we can then derive the hardness or the mean pressure in the indentation contact. So the analysis is really quite simple, and it's all done automatically in software. So when we're considering what capability we might like in a nano-indenter, I think on the left here I've given an indication of the things that I think are important in a nano-indenter. So I think you need an ability to test over a wide load range. You need the ability to test the mechanical properties as a function of depth. This is particularly important if you were interested in properties of coatings, particularly if you're interested in how obtaining those properties independent of any sublayers. And the ISO standard gives ways to do this. So that allows us to map into the surface. We also might like the ability to map across heterogeneous surfaces, such as welds or joints, and also potentially to accurately position our indentations to allow us to pull out the properties of different inclusions or different phases in the multi-phase material. And then additionally, we might like in our instrumentation to have a very high stability, which allows us to do longer duration tests where we hold the load constant and therefore look at the creep behavior in the material. So when you're considering that capability, the points to consider for the instrumentation is the maximum load that you can achieve, the ability to map in two directions or even potentially to combine those two things, and therefore to pull out hardness and stiffness in these across the material. You need very high repositioning accuracy in your standard stages to allow yourself to position exactly where you want to position. And you need very good instrumentational stability, so you need very low thermal drift. Essentially, this needs to be a very tiny fraction of a nanometer per second, ideally something like 0.004 nanometers per second or better. So this is quite an old slide now, but it illustrates typical behavior in this case, where we've looked at two different reference samples. We've done indentation tests stopping at different positions across the surface, stopping at different peak loads. So they're designed so the first one stops at 100 millinewtons, the next one 150, 200, etc., all the way up to 500 millinewtons. And this is done on two different reference materials with rather different mechanical properties. And you can see very reproducible loading curves. So all of these indentations that are taking place at different positions, their loading behavior is superimposing. And that's indicative that the instrumentation itself is very reproducible. So if you'll get variability in your data, that variability will be coming from the sample, not the instrumentation. And by using these two reference materials with very different properties, particularly a large difference in their elastic properties, so the Sapphire has a Young's modulus of about 420 gigapascals, whereas the Fusilica about 72. This therefore improves the accuracy of calibration, in this case, particularly the compliance of the instrumentation, which is, whilst it's very small, needs to be subtracted from the data to get reliable results, particularly at very high load. Okay, so to move on to an application example here. So this is a typical application example. In this case, our customer has a 2 micron thick amorphous carbon or diamond-like carbon coating that they've deposited on the silicon wafer, and they want to know the hardness and the stiffness of this coating for a tribological application. And in this particular test, instead of a typical indentation curve that I showed you earlier, here we have a load, partial unload indentation test where we load up to a preset load, and then we partially unload, and then we reload to a slightly higher load, and then we unload and go up and down that zigzag process. In this case, it's been done 50 or 100 times to a peak load of 100 millinewtons. And you can see these small unloading segments, and each of these small unloading segments can be analyzed with that unloading analysis that I described earlier, and that allows us to determine the profile of the hardness and the stiffness into this graded structure. So you can see where I've shown an arrow there, you can see a rather dramatic discontinuity in the curve, and that's where the indentation plastic stress field that you use to determine the hardness has transitioned from being completely within the coating to being partially accommodated by the much softer and more compliant silicon substrate underneath. So there's a transition there, and possibly also a small crack. So when you analyze data like this, and this slide here shows the averaging from I think 5 repeats across different positions on this slightly rough sample here, you get a regime where when the indentation depth is sufficient and load and the depth is sufficiently low, then you get a plateau, a rather constant value of the measured hardness, and this can be equated to the hardness of the coating. In this case, it's just under 22 gigapascals, which is fairly typical for a hard carbon coating. So that's because the stress field is, the plastic stress field at least, is completely within that coated layer. But as the load increases, you're getting a progressive decrease in hardness, and that's because now that stress field is increasing, and it's now a composite response being essentially accommodated more progressively by the sublayer underneath, or sublayers underneath. So then as you're going up, you're eventually starting to approach the silicon hardness of about 11 GPa at higher depths. So this so-called 1/10 rule, or Buchel rule, works very well for the hardness of materials. There is a potential issue when you try to apply that to the elastic modulus in the same way, because the elastic stress field is a more far field effect. So for a given penetration depth, the elastic stress field is extending much further. So the measured information is a composite of this substrate properties at a much smaller fraction of that coating to thickness to indentation depth ratio. So by the time you reach 1/10, there can already be quite an appreciable substrate influence, and this is particularly clear when you look at very stiff coatings deposited on very compliant substrates, or vice versa. So this is an example here of a hard nanocomposite coating of titanium nitride, nanocrystals in an amorphous silicon nitride matrix. It's a very stiff material here. In this case, it's deposited on a much lower stiffness silicon wafer. And this is an example for about 1 micron thick coating. And you can see up at a dotted line there, and actually it's about 10 millinewtons, but also this is about 1/10 of the film thickness. And you can clearly see that if you read off the value of elastic modulus there, and if you said that was the coating value, you would be quite in error. So because of the large modulus mismatch between these two materials and the far field effect in the elastic stress field. So what the indentation standard ISO 14577 says to get around this is it's better to extrapolate the values over a range of loads and extrapolate those values to 0 depth to obtain a truer value of mechanical properties. And indeed you can do that in the NanoTest software as a standard feature. So that was determining mechanical properties as a function of depth into materials. As I say, it's also quite often beneficial in heterogeneous samples to look at mechanical properties of different phases. So on the left is an example from France where a customer has been interested in putting indentations at specific phases and avoiding the smaller phases here. So you can set that up in a single experiment and go away and come back, and the instrument will automatically have positioned all the indentations in exactly where you want. Equally, if you're interested in properties potentially on a much finer scale, you can produce a grid of indentations, and you can set these up automatically. Let's say it would be over a rather small area. In this case, it's an inclusion shown on the right of a stiff inclusion in an aluminium alloy. And you can see, compared to the matrix, you get it's fairly clear. You can set this thing up. This is a very stiff inclusion. In this case, the pitch now is only 2 microns, and you can set these things up even closer than that. And automatically you get these nice square grids, and you come back and you get quantitative mechanical property information across the surfaces. So this is an example now on a bigger scale with a bigger grid. So in this case it's I think nearly 400 microns by 400 microns, and in this case there's 400 indentations done on an aerospace alloy, and on the left you see the map of hardness, on the right you see the map of stiffness, and on average the hardness and the stiffness are fairly constant, but when you do this mapping approach you can clearly see different regions of the surface are delineated with different mechanical properties, and this is due to the different microstructure and crystal orientation in this different alpha-beta alloy, essentially. So when you're doing small-scale tribological tests, you actually will get different tribological behavior depending on where in this multi-phase component you do your small-scale tribological tests. And this will impact when you're using these alloys when you're doing small-scale contacts. And this is particularly important in some of their applications, particularly in biomedical applications as well. Okay, so this mapping is particularly useful over multi-phase surfaces. So as well as these 2 examples you've seen at the top left here, it's also an example now in the bottom right where we've done 375 indents. In this case it's a staggered grid, allowing us to get more information in the phase of interest. In this case it's a brittle intermetallic phase formed between lead, copper and tin in a lead-free solder joint. You can see it's so brittle that it's even resulted in some cracking across that joint after the testing. And this is now on a machined component. You can see the work hardening that's been generated by that machining of that component there. So very quantitative information. You can also use 2 different modules. These are optional modules. And this, on the top right, you see a nano positioning, an SPM nano positioner that's been used to position indents in the middle of specific phases in a ceramic material. Or on the right, so at the bottom down here, you can use an integrated atomic force microscope image, and that allows you to look at the influence of pile-up and things like this, or in this case this is the transition of a critical load in a scratch on a biomedical alloy. Okay, so to sum up so far, the analysis of nano-indentation provides quite a wide range of different information. For time reasons I've just focused on the hardness and the stiffness information, but there's a lot of other information available. And this derived mechanical property information can be obtained, especially resolved across the surfaces of heterogeneous materials, or also profiled as depth, as a function of depth in coated or graded surface engineered materials. Okay, so this slide shows 4 indentations to different positions of a homogeneous material. This is a polymeric material, but it's rather clear that these indentation curves are completely different. So something's changed, but what's actually changed is while these tests are actually done under different environmental conditions, some materials will exhibit environmental sensitivity, so I'll talk about that. So typically, for a large majority of our tests, we might perform our tests in typical ambient lab conditions. So those would typically be something like 25 degrees Celsius, normal air, about 50% relative humidity, and we would do our tests quasi-statically. So the indentation test is where the load is applied quite slowly. But we might also be interested to understand information in non-ambient conditions, where potentially we might want to go high or low strain rate in non-quasi-static or dynamic conditions. We might want to change the gas environment we do the test in. We might like to look at the mechanical properties of function of temperature, either above or below ambient temperature, to study the effect of moisture with change of humidity in the test chamber, or even to fully immerse the samples in water, in saline or engine oil for a tribological application. So in this next section of the webinar, I'll be describing the influence of test environment, and I'll start looking at moisture, strain rate, and temperature, and I'll start off by looking at the influence of humidity. So one of my colleagues here at Micro Materials Ltd has designed a little humidity cell here which allows us to enclose a very small volume and automatically change the humidity of the electronic control system in quite a wide range between about 10 and 90% RH, and we can do that very rapidly. And that's very useful because it allows us to study the kinetics of humidifying and dehumidifying processes, which has applications in biomaterials, cements, polymers, nanocomposites. We can also use this to study the effects of humidity and tribological behavior. And in the example I showed just now, actually what we were looking at was a nylon clay nanocomposite material, and nylon 6 is very sensitive to humidity, and its composites are still to some extent sensitive to moisture. And as the curve in red was measured with a relative humidity in this small volume of 10%, and then the curves progressively fanning to the right were done under increasingly humid conditions, and you can see the mechanical properties of this polymeric material deteriorating. Its surface layers get more and more saturated with water, so it becomes softer and more compliant. Okay, so I now move on to strain rate. So this is now looked at with nano-impact testing. So we can think of nano-impact really as a complementary test technique to nano-indentation. In a nano-indentation test, we typically apply a load very slowly. Strain rate is typically something like 10 to the -3 per second, 10 to the 1 per second. And we determine hardness modulus and other parameters. It doesn't allow us easy access to time-dependent deformation in a large range of materials. What we do in nano-impact testing is we now have a dynamic test technique. So we can think about it as a high strain rate indentation test. And that allows us to access much higher strain rates in the test, right up to 1,000 per second and higher. And if we do this in a single impact, we can look at the dynamic hardness of materials, or the strain rate sensitivity of the hardness in materials. And if we do this repetitively, this allows us to look at fatigue and fracture processes and toughness of materials. So we patented this technique a few years ago, and it's very complementary to the normal nano-indentation test. It's a different module in the NanoTest, and it's becoming increasingly popular at a range of different customer sites across Europe, particularly across Europe and in North America, and customers are publishing widely with it now. So the repetitive contact that this and the speed that this technique gives you allows you to look at coating fracture resistance in a way that you just can't access this information with nano-indentation testing. So this first example here illustrates a range of 3 different impacts done with done at different positions with 6 different forces, with, in this case, a spherical indenter. This work done at Cambridge University a few years ago. And on the left of this graph, you can see there were some impacts here, and the contacts were totally elastic. This very low forcing and totally elastic behavior. As the force increases, then you get a transition to some small plastic deformation of the spherical probe. And then at 5 millinewtons in this case, then you get a transition to some cracking. And then higher load still, you're getting progressive chipping. And actually what they were able to do in this study was actually separate out fracture from delamination at the interface. By using a spherical probe, they're actually able to delaminate the coating without plastically deforming the coating or the substrate first. And that's really quite a useful thing in an adhesion test, because most adhesion tests actually are complicated by plastic and elastic deformation in the coating and the substrate. So a popular application of the nano-impact test is in simulating cutting tool tests, and therefore optimizing coatings for cutting tool tests. So this is not an impact test. This is a typical result from a cutting tool test. In this case, it's a high-speed end milling of a structural steel, and this is looking at the evolution of damage as a function of time or length of cutting for two different commercial coatings. So there's a titanium aluminium nitride, which has relatively low length of cut before the tool becomes unserviceable, and a different coating here, which is clearly much better under these applications. You get a long sort of fatigue run-in, and it's a much more gradual wear mechanism. So this is a transition to fast failure, which you don't want if you're using a coating. So this would be very poor in this application. This would be much better. So how do you design coatings to work in these applications, and how do you design coatings to work in faster speeds and therefore more productive conditions? Well, first of all, you might think about just measuring the mechanical properties of these coatings. Well, if you do that, you can there's the nano-indentation data there, and you can see in this case it's not simply a case of increasing the hardness of the coating and that therefore resulting in increased tool life, because it's clearly the opposite trend is observed. So it's not the hardness modulus ratio, but something else is going on. And if we want to understand these type of things, then we need to simulate this behavior, and the nano-impact test provides us a way to do that. And without going into great details, you see on the right now is an example nano-impact test data on those same two coatings. And you can see some really quite nice similarity between the two types of curves. So you're reproducing that fast fracture on the titanium aluminium nitride and that more gradual fatigue failure on the other one. So you have a very quick test. This is only taking at the order of a minute for each of these tests. Therefore, you can set up lots of these tests and look at the statistics of your impact processes, and that allows you really to speed up the pace of your coating development. It allows you to pre-screen promising compositions more quickly. So we can extend the power of impact testing as well. So it allows us to extend the range of strain rates, but also we can potentially do it as a function of different temperatures, and we've done that. So if I move on to looking at the influence of temperature now. So with the NanoTest fitted with a hot and cold stage, we can cover quite a wide range of temperatures, down to about -20 and up to about 750 degrees C. And we can do these type of tests with controlled heating of the sample stage and the indenter, or controlled cooling of the sample stage and the indenter. And this is critical for data reliability. So this slide shows what we consider to be the wrong way to do things, where you can try to cut a corner by only heating the sample stage and hope that if you leave it long enough in contact, then you might get thermal equilibrium, and then you can do a test. So this is an example from a study done from Nottingham University a few years ago, where they've simulated what happens when you have a conductive sample in contact with a heated diamond indenter, and you leave it for a long time, in this case 8 hours. But after this long equilibration period, there's still a large temperature gradient, and this large temperature gradient would really be quite problematic if you were trying to do an indentation test. So the solution to this is to actively heat the indenter as well as the sample, and this ensures that you achieve an isothermal contact, and this can therefore result in either very low drift or if you set it up with a bit more care, then essentially in zero drift at very high temperatures. So this is slide shows the hardware and how you do this. So we have an advantage in the horizontal loading in the NanoTest, that our heat flow is going away from the displacement electronics by convection. We have active heating on the indenter side, active heating on the sample side. It's not shown here, but we'd have a surface thermocouple as well, providing a very precise measure of the surface temperature. And we've patented both the stage design and also the temperature matching, allowing for the different thermal masses of the indenter and the sample. So it's a horizontal loading configuration with a separate active dual heating of the probe and the sample. When you do that, you can really get some quite nice data. So this is an example of some data we've done over the years, combining, looking at 3 different coatings, hard coatings done again for cutting tool applications. If we focus just at room temperature, we can see this titanium aluminium nitride for this particular supplier has been really optimized by having high room temperature hardness, but its high temperature stability is not so good. This one here, small compositional change presumably, potentially increasing the fraction of aluminium there, has lowered its hardness at room temperature, but nevertheless has given it much better stable hardness at high temperature. And indeed, you can multi-layer, and that may also give you a combination of high room temperature hardness with high room hardness at high temperature. So you can see where the high temperature nano-indentation can provide access to some really reliable data, which allows you then to understand the high temperature mechanical properties. And if you were to do a cutting tool test where your test temperature would be 500 degrees or more due to frictional heating, then really this is the important hardness of the coating. It's not so critical what it does at room temperature. It's in terms of its wear performance in the application, then it's the high temperature mechanical properties that are more important. So testing at room temperature isn't always a good guide for performance at high temperature. It's good for characterization, but not necessarily for performance optimization. So another application in this example here, this is from Georgia Tech. Now with stability of your instrumentation, now you can look at time-dependent processes. So this is an example of a glass ceramic seal material in a solid oxide fuel cell, and looking at the time-dependent deformation that occurs at constant load as a function of temperature. So you can see here at room temperature at 25 degrees, there's very little time-dependent deformation. As we heat up to 550 degrees Celsius, we're starting to get some thermally activated creep processes, and then as we increase just 100 degrees more, 200 degrees more, now we're getting a dramatic increase in creep. So this is the sort of information you can access now with high temperature indentation testing. And if we look at comparing materials now, so this was part of a study, in this case, as I say, by Georgia Tech, and they were interested in looking at the high temperature creep behavior and also the high temperature stiffness behavior of these glass ceramic seal materials after a prior aging at 800 degrees before the testing was commenced. So this shows the results of high temperature nanomechanical tests done with the NanoTest after aging samples for 4 hours or 80 hours. And again, we can see at room temperature these samples are rather similar, but as the temperature increases, you can clearly see some benefit for aging for a longer period. Okay, so moving on now to finish off with a little bit on nano microscale tribology or nano-scratch and wear testing. So we can do a range of different tribological test techniques with the NanoTest. We have a scratch module that allows us to do ramped and progressive load scratch tests and look at friction and look at critical failure events. We also have a repetitive scratch testing capability in that module. Allows us particularly to look at low cycle fatigue behavior. And that allows us to decrease the contact pressure a little bit and start to look at fatigue processes.
But what's particularly interesting is we also have a capability for looking at fretting or reciprocating wear, and this allows us to look at much higher cycle tests, and therefore to look at much lower, more representative contact pressures, more representative the pressures that might be experienced by a coating in an application. And then, so the combination of these things really allows us to understand the tribology and the coating behaviour over a range of different severity of tests. Okay, so to move on to scratch testing. So we can use it to look at novel materials here. So this is an example of some nano-scratch research done at Oxford University, where they were looking at basically how graphene films flake at higher load, and also they looked at friction. In a nano-scratch test, particularly moving on now to a harder coating now, in a nano-scratch test, what's particularly useful from an instrumentation point of view is to design an instrumentation with a high lateral rigidity in its loading head. So it allows you therefore to test rough samples without your data being unduly affected by this high roughness. And this is an example now showing overlaid friction forces as a function of load on a tool steel and a tool steel surface with two different thicknesses of titanium nitride coating, and you can see clearly again the friction forces prior to the failures are very consistent, so you get a very nice friction coefficient out of that. Then you're getting these rather brittle failure events in the steel, and you're getting these brittle failure events increasing the friction with the coatings. And you can see you can measure friction right up to the top force range of the instrumentation. So this high lateral rigidity is useful as well if you're going to do some rather extreme wear testing. So this is a highly loaded contact with a small spherical probe on a Sapphire single crystal. And here you can see an illustration of the progressive evolution of this wear in a 10-cycle test. And this is the first, so the load is ramped between here and here. After 100 microns to the end of the test, it's a constant load. And on each progressive cycle, you're getting more and more damage, gradual damage, and then in this fourth cycle, you're getting an evolution to most of this region now is being progressively worn away, and there's a sort of abrasive or third body wear process going on there. So if I finish up with this fretting or reciprocating wear module, so it allows us to reciprocate that contact. So the example on the bottom right there is actually for a biomedical alloy, and part of a study done where the tests were performed at a range of different loads, and they could understand weaknesses between different alloys that and used to optimize different compositions for hip joints replacement. So when we designed this test, we noticed that there was essentially a measurement gap in terms of forces, displacements, and pressures between using an AFM as a tribometer and using a conventional tribometer. So we developed the nanoscale reciprocating wear or nano-fretting technique to fill that gap. It has a range of different applications in wear-resistant coatings and biomaterials and MEMS. It allows you to study really the fundamentals of friction and to do tests over quite a wide range of different loads and contact pressures and number of cycles and frequencies. So this is an example, in this case from a university in the UK, looking at fretting of a hard carbon film. In this case, the diamond has been replaced by a large radius ruby ball. And in this case, the amplitude of the fretting is very small compared to the radius of this ball. And here you're getting a classic fretting scar with a central stick zone and all this little fretting wear occurring around the edge of this little contact zone. You're getting under high load, getting really high numbers of cycles that are possible. And under different conditions, in this case they've gone for lower load and much higher track lengths or higher amplitude, and they're getting a transition to a sort of grooving wear. So you're getting a transition from partial slip to gross slip. And the key point about these things is that you can run these things under very low contact pressures compared to conventional nano-scratch testing. So it allows you to access part of the tribological behaviour. Okay, so I hope you found that interesting. And to summarise, there's more information that you can get out of characterisation of mechanical properties of materials at the nano and micro scale when you are not just interested in the hardness and the modulus, but you consider some of this other information, such as their tribological behaviour and their sensitivity to different conditions. So the NanoTest Vantage has been developed with we think, a greater range of capability for these different nanomechanical test techniques. So nano-indentation, nano-scratch, nano-wear, impact and fretting, and the ability to perform these in a range of different test environments, higher low temperatures in different gases, liquids or different humidities. And therefore it provides essentially a more effective combined capability for providing more complete and reliable characterization of materials, and therefore it's more useful in optimizing materials and coatings for new applications. Okay, thank you for your attention.